Hello students. In this class, basically I am going to discuss the mass parabola for the isobaric family whose A number is an even number. In the last class, I have discussed the mass parabola formation for the isobaric family having A number equal to odd number, for which A number is odd. So in case of isobaric family for which A is an even number, in place of one parabola we will have two parabola. In this case, rather than one parabola we will have two parabola. For example, here we have, suppose A number is 64, so A number is an even number, so and it will have two type of nuclear isobars. Few isobars will be even isobars, and other family members of this isobar will be odd isobar. So basically, for this isobaric family for which A is even, we will have two mass parabolas. One will be for the family members of this isobaric family which are odd, and other parabola will be for the family members which are even nuclei. So basically, what is the mathematical reasoning for this? We are aware that mass of the nuclei MZA, it can be represented as AA plus XZ plus YZ square and plus minus delta 1. This is the expression for the mass of a nuclei having Z number. This Z number is here, charge number, this is the mass number. Basically, in earlier case when we have A is a odd number, we are basically using the A number, odd number for the isobaric family. Then this delta 1 was 0. This delta 1 is corresponding to pairing energy. This was 0 for the even odd or odd even nuclei, and if A is a odd number, so automatically odd A number will give rise to two type of nuclei, either odd A nuclei, odd even nuclei, or even odd nuclei. For both these type of nuclei, this delta will be 0. But here, when A number is even, we are aware that this delta 1 will not be 0. Rather, this plus sign will exist for odd nuclei. We have discussed in earlier class for odd nuclei, and this minus is for even nuclei. So due to this reason, when we will plot this mass M, as a function of Z, if we plot the mass of the family members of a isobaric family as a function of Z, then we will find out two plots. Here we will get two parabolas or two plots. One will be corresponding to odd nuclei, another will be for even nuclei. Here even I want to make you clear that if we have even A nuclei, then two type of nuclei are possible, either even Z, even N nuclei, even Z, even N nuclei, or odd Z, odd N nuclei. So these two type of nuclei may be present when A number is even number, and corresponding to these two type of nuclei, this is even nuclei, we are aware that pairing energy is with plus sign, while for odd nuclei pairing energy is with negative sign. But here when we have derived these sign, they are changed due to the minus sign. Plus was become minus and minus will become plus. So this plus is here for odd nuclei, this minus is for even nuclei. So due to the presence of these two signs for odd nuclei and even nuclei, we will have two mass parabolas. Here you can also observe one thing. you can also observe one thing, that mass of the ordered nuclei, mass of these ordered nuclei, it will be greater. It will be greater than mass of even nuclei. Because due to this plus sign, because plus sign is here, so automatically mass of the ordered nuclei will be higher as compared to mass of even nuclei. So due to this reason, this upper parabola, this will be for ordered nuclei. This upper parabola will be for ordered nuclei, and this lower parabola, this one, it will be for even nuclei. Here we have plotted, we have taken the example of A equal to 64 family. We are using an isobaric family for which A number is 64. So here we have 5 members, and you can observe that all the 3 members which are ordered nuclei, this 27 CO64, 29 CU64, this 31 GA64, they are ordered nuclei. They lie on the upper parabola, while the nuclei which are even like 30 ZN64 and 28 NI64, they lie on the lower parabola. From this we can also conclude one thing, because mass of these nuclei, ordered nuclei, is higher as compared to these nuclei which are lying on the lower parabola. So these nuclei will be more stable as compared to ordered nuclei. So in general, you will find out very few ordered nuclei exhibit the stable structure. Only there are few exceptions for this, and these exceptions are 1s2. 1s2 is an example, 7n14 is another example, 3li, 6 and 5 B10. These are the examples these are the examples of ordered nuclei, but still they are exhibiting the stable structure. But for these nuclei, these are low A value nuclei, and these are low value nuclei, or you can say these are lighter nuclei, and they do not come under the purview of liquid drop model. So they are lighter nuclei. So what is the reason for this? They are lighter nuclei which do not come under the liquid drop model. So these are the exceptions, but because of being lighter nuclei, they do not come under the liquid drop model. So from here, we can also conclude one important thing, that the nuclei which are lying on this lower parabola, which are even nuclei, they are more stable as compared to ordered nuclei. Apart from this, here you can also observe one thing. Here you have 2 nuclei on the lower parabola whose Z number is differed by 2. Here on the lower parabola, for the even parabola, even nuclei parabola, we have 2 isobars whose Z number is differing by 2 units. They lie at the bottom of the lower curve. They are lying at the bottom of the lower curve. So they are forming a pair of stable nuclei. So here these 2 nuclei, they form a pair of stable nuclei. In earlier case, we have only one parabola, and the nuclei which was at the lowest point of the parabola, that was the most stable nuclei. But in case of even a nuclei isobaric family, at the bottom of this even mass parabola, basically we will have a pair of stable nuclei, and this pair is known as stable isobaric pairs. This is known as stable isobaric pair. This is known as stable isobaric pair. And these are the most stable nuclei in this family. These are the most stable nuclei in this family. Now here, in this example, one can observe one thing. Suppose this 27CO64, which is less stable as compared to this nuclei 28Ni64. So basically, to achieve the stable nuclear configuration, this nuclei can emit a beta minus particle. It may emit beta minus particle, and by emitting beta minus particle, it will convert into this more stable nuclei. Similarly, this nuclei which is at the bottom of this upper parabola, this will not be a stable one. Suppose it want to achieve the stable configuration, it has two options. Either it will emit beta plus, so by emitting beta plus particle, it may convert into 28Ni64, or it may also emit beta minus particle, and by emitting beta minus particle, it can also convert into 30Zn64. Both are the stable nuclei, 28Ni64 and 30Zn64, both are stable nuclei. So basically this bottom nuclei, it can convert into these two, either emitting beta plus or beta minus particle. Similarly, this nuclei 31Ga64, it can undergo beta plus emission, and it may convert into a more stable nuclear configuration. So here it will be beta plus. Why they are emitting beta plus and beta minus, we have discussed in earlier case when we were discussing single parabola. Now, next question arises, how much energy will be released or absorbed in these beta plus emission and beta minus emission? So for this, if we want to calculate the Q value of these beta processes, then what we need? First we need the mass of the most stable nuclei, and we are aware that the Z number of most stable nuclei is given by minus x upon 2y. This is a formula we have derived in earlier lecture, that the nuclei whose mass number is A but whose Z number will be Za, and Za will be equal to minus x upon 2y. This nuclei will be the most stable nuclei. So what will be the mass of the most stable nuclei? That will be mza, A. And this will be AA, mass number is A, plus this will be XZA plus YZA square. And here we can have two signs. But can you tell me that in case of most stable nuclei, either we will take plus or we should take minus sign? Which signs we should use in this expression for the most stable nuclei? We are aware that the most stable nuclei will have the lowest mass. It will have the highest binding energy and the lowest mass. So basically, the nuclei with this sign minus, that will have the lowest mass. So this will be the mass of the most stable nuclei here in this case. Now with the help of this, substitute in place of this x, replace this x by minus 2y ZA. So here it will become AA minus 2y ZA square plus YZA square. And this will be minus delta 1. So this will be AA minus YZA square and minus delta 1. Now what will be take the difference between these two equations? Mass of, we can write down the mass of the different family members of the isobaric family in terms of the mass of the most stable nuclei. So to write down this in terms of this, we will subtract these two equations, this one, this equation and this equation, what we will find out? We will find out MZA minus MZA comma A. This will be this AA, this will be cancelled out by this, and what here we will have, this will become equal to XZ plus YZ square plus minus delta 1 and minus plus YZA square, and this will become plus delta 1. This will be the expression. Now again replace this x by minus 2yza. So I will write here minus 2yzza plus yz square plus yza square plus minus delta 1 and plus delta 1. This will be my expression. This will be my expression. So this expression will be equal to minus y z minus za square, and this will be plus delta 1 and plus delta 1. Now this plus sign is for odd nuclei. So for odd nuclei, now we will get two expressions. One for odd nuclei. So for odd nuclei, this MZA, take this sign to the right hand side. So this MZA will become this MZA. This will be equal to MZA A minus Y Z minus ZA square. For odd nuclei, this will be plus sign, so this will be plus 2 times delta 1. So this will be plus delta 1 plus delta 1, this will be plus delta 1. While for even nuclei, this mass of a nuclei of this isobaric family can be written as MZA comma A. This will be minus Y Z minus ZA square, and here for even nuclei, this minus sign will be here. So this minus sign, this plus sign, they will be cancelled. So these are the expression of the masses of the isobaric family for even type or odd type of nuclei. Now with the help of these two formulas, we can find out the Q values of beta plus minus decay, either beta plus decay or beta minus decay. So one by one, I am going to calculate the Q values of beta plus decay and beta minus decay. So first, Q values of, here we will find out Q values of beta minus decay. In this beta minus decay, suppose we have a nuclei whose Z number is Z. This is the Z number of parent nuclei, and this is converting into a nuclei whose Z number will be Z plus 1. And here beta minus decay is taking place. Now there can be two cases. First case will be when this Z is, suppose this Z is odd number. Suppose the parent is odd Z nuclei. Then automatically daughter nuclei will be even Z nuclei. It will be even Z nuclei. So what will be the Q value of this process? This will be Q beta minus. This will be mass of the parent nuclei Z minus mass of the daughter nuclei Z plus 1A. So this will be the Q value of this beta minus process. Now, this is odd nuclei. From here, you should remember that this is odd nuclei. odd nuclei. This is even nuclei. Even nuclei. So substitute this expression with the help of this. MZA will be equal to this one. So this will be MZA, comma A minus Y Z minus ZA square. This will be plus 2 times delta 1. And this will be minus. This is even nuclei. So for this, I will use this expression. So this will be equal to MZA, comma A minus Y Z plus 1. This is Z plus 1. So substitute here Z plus 1. Z plus 1 minus ZA. And this will be square. This will be square. So these two terms will be cancelled out. And when you will expand, as we have done in the earlier case, you will find out the expression. You will find out the expression equal to 2y here with plus sign, and here this will be ZA minus Z, and this will be minus half. This will be minus half and plus 2 times delta 1. This will be the expression for Q beta minus. This will be the expression of Q beta minus. Now if you want to find out, if we want to find out the Q values of beta plus decay, if we want to find out the Q values of beta plus decay, then our equation will be, now Q values of beta plus decay, then here it will be Z. This is the Z number of the parent nuclei. This nuclei will convert into Z minus 1 nuclei by emitting beta plus. So what will be the Q beta minus or Q beta plus, sorry. Here it will be Q beta plus. This will be equal to MZA minus MZ minus 1, comma A. Here this is odd nuclei, or you can say this is odd nuclei. This is odd nuclei, or this is even nuclei. This is even nuclei. Then what will you get when we will do this? When we will do this calculation for Q beta plus, when you will do this calculation for Q beta plus, then here first this is odd nuclei. So Q beta plus will be equal to, this will be, first is odd nuclei. So we will use this expression MZA, comma A minus Y Z minus ZA whole square plus 2 times delta 1 minus, this we will use this for even nuclei. So this will be MZA, comma A minus Y minus, this will become minus plus. This will be Z minus ZA square, and here there is no delta 1. There is no delta 1. On substituting these values, this will be cancelled out by this one. And when we will expand this square and this is here, what will be this? This will be, this is not Z minus ZA. This is not, basically here, what is this? This is Z minus A. So we have wrongly written here. This will be Z minus 1. This will be Z minus 1 minus ZA square. This will be the express. And when you will expand these squares, you will find out the final expression of 2y, and here you will have minus sign ZA minus Z minus half and plus 2 delta 1. So this will be the expression of Q beta plus. So if we combine the earlier expression of beta minus and beta plus, so this will become like this. This will be the expression for Q beta plus minus when the parent nuclei, here parent nuclei, when parent nuclei is odd nuclei, and deuter nuclei is even nuclei. So this is the expression of Q beta plus and Q beta minus processes. These are the Q values of beta plus and beta minus processes when the parent nuclei is odd and the deuter nuclei is even. Now there can be another case. Suppose now we want to find out the Q values of beta plus minus processes when parent nuclei is even nuclei, while deuter nuclei is odd nuclei in this beta plus minus emission. If parent type of nuclei is even and deuter nuclei is odd nuclei, in that case again you will follow the same processes, you will use these two formulas, you will follow the same method, but first when you will write this equation like this, Q beta minus plus, this will become mass of this ZA. This is even nuclei. Minus, this is the parent nuclei, mass of the parent nuclei. This is even nuclei minus mass of Z. If minus emission is there, then plus will be here. If my plus emission is there, then it will be minus Z plus minus 1A. These are the masses of deuter nuclei, and these deuter nuclei are odd nuclei. So whenever you are substituting this expression, you will choose this one. This is the expression for even nuclei. You will substitute this expression here, and you will substitute this expression here. There will be only one change here. This will be in place of Z, we will write Z plus minus 1. But here what is important, when first you are going to write this minus this, then this term, this plus 2 delta 1, it will become minus twice delta 1. And in this case, the final expression for Q beta plus plus, we will find out this expression will be similar. It will be nearly similar, but there will be only one difference here. That in place of this plus 2 times of delta 1, we will have minus 2 times of delta 1. So this is the expression of the Q values of beta plus and beta minus processes when parent nuclei is even nuclei. So for this type of processes where parent nuclei is even nuclei and deuter nuclei is odd nuclei, we will have this minus 2 times delta 1. While if the parent nuclei is odd and deuter nuclei is even, then we will have plus 2 times delta 1. Otherwise, these formulas are very similar as we have calculated or we have find out in the last class. You can remember this from the last class. Only you have to add up either this 2 delta 1 if parent nuclei is odd, or you have to subtract this minus 2 delta 1 if the parent nuclei is even. So this is all about the mass parabolas for odd A type isobaric family or even A type isobaric family. In case of odd A isobaric family, we will have a single mass parabola, while in case of even A isobaric family, we will have two mass parabolas.